Okay, we're back in our second video talking about events, and in this video we're going to talk about unions, intersection, complements, and all that stuff. So if you've ever taken a class where you talked about set theory, this is going to look very familiar. It's basically just the same ideas dressed up in the language of probability. So these are really what we're talking about here is ways of putting together events to make new events, and it's kind of like an analog of the arithmetic operations like addition and subtraction and taking a reciprocal, things like that. Two of the main operations we're going to look at are what are called binary operations, which means you take two events and you get a new event out of it. And one of them is what's called unary operation, which it's kind of like the reciprocal or taking the opposite. You start with one event and it just gives you another event. But these are the three main operations to perform on events. So let's just start in. The union. The union of two events, E and F, in a sample space is going to consist of all outcomes in S that are in E or in F or in both. So it's very important you understand that it's possible for the outcome to be in both of them. It's still going to be in the union. The ordinary English meaning of the word or doesn't really match with the math meaning. Normally, if somebody says, do you want this or this, they mean, do you want one or the other, but not both. So if a waiter comes up to your table and they say, do you want soup or salad with that, usually meant, do you want soup or do you want salad, but you don't get to have both. That's not allowed. But it is allowed in math. So this is what's called the inclusive or, because you're including the possibility that both happen. And the other kind, the ordinary English definition, is called the exclusive or, which is different. So just for the rest of the class, whenever you see or, just assume by default that it means the inclusive, that it allows both possibilities. The way you can think of the union in terms of outcomes, if you think of each of the events as kind of like you're cooking in the kitchen, and there's two pots and they have ingredients, food ingredients in them, and those are the outcomes. The union is kind of like taking the two pots and just throwing them together in a third big pot. So you're making a big stew in a big pot, and you have the two original pots of ingredients, and you just toss them all together into one pot. Now, it's true, there may be ingredient that's in both pots. Maybe you have some salt in both of them. Salt in one, salt in the other. Well, you mix them, you put them into the big pot, there's still salt there. But it doesn't make sense to say that you have salt twice. There's just salt. So if it's in both, it's just in the union. It's not in the union twice. As we write this, this looks like a U, but it's not quite. It's more of a cup shape, like the bowls you eat at the Japanese restaurant, that kind of shape when you eat soup. So that kind of cup shape, and we say E union F. If we phrase this in the language of occurrence, there's a really nice way that this rolls off the tongue. It says E union F occurs exactly if E occurs or F occurs or both. Okay. I'm going to go through all three definitions and then we'll do some examples later. So let's get to the second one, the intersection. Intersection of two events consists of all the outcomes that are in both events. So you have to get into both events to be in the intersection. And the notation here, you just turn that bowl-shaped U upside down, and it becomes E intersect F. So we say E intersect F. And we say that E intersect F occurs exactly if both E and F occur. So it's the outcomes that are common to both events. Finally, the complement of an event consists of all the outcomes in the sample space that are not in E. So it's really important that you keep in mind which sample space you're in. You can't just talk about the absolute complement without reference to some kind of, in set theory you call it a universal set. But here it's the sample space, so we're talking about the complement relative to the sample space. So everything in the sample space that's not in the event. And we're going to write this as E with the solid bar above it. But there's other notations that are common as well. There's E with the superscript C, E with a superscript kind of prime symbol or apostrophe. All three of these are pretty common. They all mean complement of the set or complement of the event. So, in terms of language of occurrence, E complement occurs exactly if E does not occur. So, we can draw some pictures that represent each of these three. And these are what are called Venn diagrams. And a Venn diagram is a way of kind of showing the relationship between different sets. And if you look at these two, for instance, so you've got the whole sample space is represented by this rectangle. So you can imagine the outcomes are like points that are inside the sample space, inside that rectangle. The events are going to be written as these circles, and if an outcome lies in the interior of that circle, then it's in the event. If it lies outside, then it's not in the event. So what gets into E? Well, it's all the outcomes that are inside E. And what gets into F? It's all the outcomes that are represented by being in F. So the union. What do you do for the union? Well, it's everything in E, so certainly we have to have this region shaded and this region shaded here. Those two. But also everything in F. So we have to have this region and this region, but we already shaded that, so we don't have to really shade it again. It's already shaded. So we end up with these three regions end up forming the union. So that's what the union looks like in a Venn diagram. The intersection, there's only one of those regions that's common to both. That's the little bit of overlap between the two there. So every outcome that falls inside that region there is in E and in F. So that's the intersection. And the complement is everything outside, so it's everything in the exterior of E. So any outcome whose point is outside E, that's going to be in the complement. Okay, so let's look at some specific examples. This can seem a little abstract first. Okay, here we go. So let's just take a sample space, just 10 outcomes, just label them 1 through 10. Now here's a Venn diagram. There's E, there's F, and you can see I've put the outcomes as dots and I've kind of labeled each of them from 1 to 10. So, who gets into E? Well, if you look which points are in E, it's 5, 6, 8, and 3. So 3, 5, 6, 8. And who gets into F? 6, 7, 8, 9, 10 makes up F. So the union, so to find the union, you're going to go to each of these events, and it only has to be in at least one of them. So if it shows up in just one of them, it gets in the union. So certainly 3, 5, 6, 7, 8, but also 9 and 10. So 3, 5, 6, 7, 8, 9, 10. And you notice that's exactly what these three regions here, just like in the Venn diagram that made up the union, those are the points that are in those regions. The intersection is just the overlap here. There's only 2 outcomes in that overlap. There's only 2 numbers that show up in both events here, 6 and 8. So that's the intersection. And the complements, so for the complement of E, we can go, and probably the simplest way here is just to look at the elements, the outcomes that are listed in E, and it's just everything that's not there. So 1, 2, what are we missing? 4, 7, 9, and 10. And for F complement, well, 1 through 5. 1, 2, 3, 4, 5. Now, these are the basic events you can generate from E and F. But you can do other things as well. You can combine these in ways on top of each other. So For instance, you could take E union F and say, what's the complement of that union? So let's see. E union F complement. Well, if this is E union F here, what does not get in there? Who doesn't get in there? Well, we're missing 1, 2, and 4. So that's the complement of E union F. There's another event we could ask about. What about the complement of E, so this event, and the complement of F, this event? What if we tried to intersect those together? What's in common with those? So look at these two events. 1 is in common, 2 is in common, 4 is in common, and that's it. So 1, 2, and 4. Wait a second. That's the same thing we got up here. When we took the complement of the union, we got 1, 2, and 4 as well. That's kind of a coincidence. Well, turns out it's not a coincidence. This is actually an example of a general law in an area of algebra called Boolean algebra. It's called De Morgan's laws, and if you ever have to study computer design or electronic circuits, or you take a logic class in philosophy department, you'll learn a lot about Boolean algebra and De Morgan's laws. This is one of a pair of statements. It also says that if you take the complement of the intersection, it's the union of the complements. It's called the dual statement. But we're not going to get into, all the different results you could prove in Boolean algebra, because that's not really what we're interested in. But just know that this is an area, a subject in math that extends far beyond probability and statistics, and has applications to all sorts of other subjects, especially computer science. If you're a computer science major, you're going to see this again many times. Okay. Might not be phrased in terms of unions or intersections. It might be a little bit different notation and stuff, but you see it again. Okay, so another example, this time maybe not as artificial. Select a card at random from a 52 card deck. So remember, a 52 card deck has the 4 suits: hearts, diamonds, clubs, and spades. And each of the suits has 13 ranks, from ace all the way up to king. Or I guess I could start at 2 or deuce and all the way up to ace, but let's say we're playing low ball. Start at ace. So let's look at these two events. Select a heart. So one event E, select a heart. Event F, select a 7. Okay. So what would the union and intersection be here? And I'm just going to give a verbal description for the first one, E union F. E union F is select a heart or a 7. And notice I didn't put or both, because I said you should start getting used to assuming that or means inclusive. So when you see or, it means or both. So we select a heart, or we select a 7, or maybe we got both. The intersection, E intersect F, there's only one card in the whole deck that's both a heart and a 7. Of course, that's a 7 of hearts. So this is one outcome. So I'm just listing it in set notation, just putting the card inside set braces. E complement. Well, what's a complement? If you don't get a heart, you must have gotten one of the other 3 suits. So the complement of E we could describe as selecting a club, a diamond, or a spade. Okay, one of the other 3 suits. And the complement of F is selecting one of the other ranks. So ace, 2, 3, 4, 5, 6, 8, 9, 10, jack, queen, or king. Okay, we're going to come back to this a lot, this example, when we study when we look at conditional probability and independence. This is going to be a good example to look at. So the next video we'll go further along in talking about these things. We need to talk about, we're going to start with the addition rule here. So there's several formulas that we have for counting things, and that's what we'll do in the next video. Okay.